Now discuss about Peterson solution. Okay. This Peterson solution provides a solution to critical section problem. Okay. So this provides a solution to critical section problem. Okay. But let's see what are the points. It is a software based solution. Okay, it is a Peterson solution is a software based solution which is only applicable for two process system. That means it only takes two processes, either P0 and P1, or it will take Pi or Pj. Okay, P0 or P1 or Pi or Pj. Okay, so there are two shared variables are there. Flag is one shared variable which is of boolean type. Okay, and term is one more variable which is of int type, which is of int type. Assume that if you take Pi and Pj as the process names. Okay, as the process names. So if you take Pi and Pj, if you take I value equal to 0, okay, then j value equal to 1 minus I. The formula for j is 1 minus I. That means if I value equal to 0, j value equal to 1. If you take I value equal to 1, then j will become 0, because 1 minus 1 will become 0. Usually we will take this way. Okay, so the concept of Peterson solution is very simple. Assume that there are two people in a house, P0 and P1. Assume that these two are brothers. Okay, these two are brothers, and these two have a common computer. Okay, a common computer, shared computer. Okay, before, and these two people, okay, let us take P0. P0 wants to use computer. P0 wants to use this particular computer. Okay, so before using this particular computer, P0 will ask P1. Okay, P0 will ask P1, do you want to use the computer or not? Okay, if P1 says yes, I will use the computer, then P0 allows P1 to use the computer. P1 to use the computer. Okay, the concept is, if there are two processes, P0 and P1, and there is a shared resource, there is a shared resource, then process P0, before executing this particular shared resource, it will ask P1, process P1, if you want to execute, use this particular shared resource. Here the shared resource, we'll put it onto critical section. We'll put it onto critical section. Okay, so P0 wants to execute critical section, and at the same time P1 also wants to execute critical section. So before executing critical section, P0 will ask P1, do you want to execute critical section? If P1 also ready to execute critical section, then P0 allows P1 to execute critical section. Once P1 come out of the critical section, executes it and come out of the critical section, then P0 will enter into critical section. Okay, so that will be the concept. Now look at the code, pseudocode of this particular code. Okay, so this particular Peterson solution provides, okay, a solution to critical section problem. Okay, so every critical section problem must have to satisfy three requirements. First one, mutual exclusion. Second one, progress. Third one, bounded waiting. Okay, right? So here the mutual exclusion, this is the code, okay, that will give you mutual exclusion part, and we will call it this one as entry section. Okay, so we'll write mutual exclusion code in entry section. Then this particular line will be our exit code, will be our exit code. This particular exit code provides both progress as well as bounded waiting. Okay, how they will provide progress and bounded waiting, we'll see that. Okay, so here we need to uh, remember two points. First one, there are two variables, of flag and term. There are how many variables? two variables. So flag is a boolean array variable. Flag is a boolean array variable. Whenever a process pi or pj or p0 or p1, okay, p0 or p1, so I will take I value equal to 0, j value equal to 1, so this will be p0 and this will be p1, so it's a flag. Whenever a process wants to execute critical section, it will set flag of I equal to true and flag of j equal to true. Okay, what is mean by that? Flag of I equal to true or flag of j equal to true. What is mean by flag of I equal to true? Pi wants to execute, that is ready to execute critical section. Flag of j equal to true means pj is also ready to execute critical section. Okay, now this particular turn value at any point of time, flag of I equal to true and flag of j equal to true. But look at here, there is no turn value. What is turn? Turn will decide which process to enter into critical section. The variable turn will decide which process will be entering into critical section. There is one more statement, flag of I equal to false. Flag of I equal to false. What is mean by that? Process pi does not want to execute critical section because it is executing some reminder section. Okay, non-critical section code it is executing. Similarly, flag of j equal to false means pj doesn't want to execute critical section. Okay, now let's see the code. This is the code for pi and this is the code for pj. Okay, now we are using time sharing system, so I will take at any point of time, any point of time quanta, maximum there is one statement that will be executed. Okay, maximum one statement that will be executed, because all are assignment statements only. Even if we convert it into assembly language, that will be only one statement in assembly language. Okay, let's see. I will give the number 1 2 3 4 and 5 6 7 8. Okay, so what I will do here, let's see, let's execute statement by statement. First we'll execute one statement of pi, then we'll execute one statement of pj, then we'll come to here, then we'll go to here. Now look at carefully. First the statement is flag of I equal to true. Okay, so I'm writing pi value flag of I equal to true. Okay, then after 1 I'm executing 5. So what is 5? Flag of j equal to true. So I'm writing flag of j equal to true. Then I will execute 2. Okay, this one. So this is executed, this is executed. Then I will come to that turn equal to j. So pi sets turn value to j. Okay, then it will go come here and execute 6, and it will set turn value to I, turn value to I, because the value is replaced here. The value is replaced here. Now after that it will come to pi, because of time count expired, it will come to pi, then executes this particular statements. And you need to observe this particular statement, after while there is no statement but a semicolon is here. Okay, there is no statement but semicolon is here. You need to remember that this particular no statement semicolon, okay, that means if this condition is satisfied, okay, the statements here will be executed, while loop will be executed. But there are no statements in the while loop, it keep on executing itself. Okay, until and unless this condition will become false. Okay, the condition while condition has to be broken. Now let's see what will happen. Okay, so now look at the values, look at the values. Flag of j, what is flag of j? It's a boolean variable, so flag of j equal to true. And is turn equal to j? No, turn value equal to I. So what we will do, it is false. True and false, which will give you false. While false means while loop will be broken. Okay, while loop will be broken and it will execute critical section. While loop will be broken and it will execute critical section. Now pi is in critical section. Which process will be in the critical section? It is pi. Now after executing while, okay, at any point of time only one statement will be executed. Immediately the control will be goes to step number 7. Correct? So here also the comparison will be done. So flag of I is flag. What is the value of flag of I? True. So it is true. But what is the value of turn? Is turn equal to I? Yes, turn value equal to I. So the condition is satisfied, the while condition is satisfied. So there are no statements to execute, and while condition is satisfied, again it will execute while. Again it will execute while. It will not enter into critical section. It will execute again until this while condition is broken. Okay, it will not enter critical section. Then again after time quanta, the control will come here and execute critical section. If it is come out of critical section, it is okay. But again, if the time quanta expires, again it will go here and check the condition again. Again it is true and true, flag of I equal to true, and turn equal to I. Again it will be blocked, PA will be blocked to enter into critical section. And assume that here, after this one, okay, after executing critical section, it will come out and started executing this particular statement, flag of I equal to false. Now I am setting this particular flag of I equal to false. Now the control will goes to again while loop. Now look at here, previously flag of I equal to t, now the flag of I equal to false. Look at here, flag of I equal to false and true, it will become false. If while loop, this particular thing, false and true will become false, the while loop will be broken and it will enter into critical section. Now which process is in critical section? PJ. So until PJ is in critical section and come out of the critical section and set this particular flag value to flag of j equal to false, PI will be restricted to enter into critical section. Okay, so currently PI will execute its remainder section. So this is how, that means when PI is in critical section, PJ will stuck in while loop. Okay, when PJ is in critical section, PI will stuck in while loop. PI will be stuck in while loop. So while loop, we are implementing it as a mutual exclusion that guarantees that only one particular process will enter into critical section. Other process has to wait to execute. Now let's discuss about progress and bounded waiting, because this particular part of code is providing mutual exclusion. The exit section code, this exit section code provides the property of progress and bounded waiting. How? Because until and unless this particular process PI comes out and execute this particular flag of I equal to false, flag of I equal to false, PJ while loop will not be broken. PJ's while loop will not be broken. Okay, that means if two process Pi and Pj are in the race, Pi and Pj are in the race, after Pi comes out, Pj will be executed. That means the after Pi, Pj will be selected to execute. Similarly, after Pj, then Pi will be executed. That means it is selecting the next process, as well as it is telling that after the Pi turn, Pj will be executed. After the turn of Pj, Pi will be executed. Okay, so this way it can, this particular exit section code, flag of I equal to false or flag of j equal to false, will give you both progress and bounded waiting. But the problem with this particular Peterson solution is it does not work for modern computer, because the solution is suitable for only two process. Okay, so all the modern computers will work with multi processors. It will not work for modern computers. And similarly, we cannot implement Peterson solution for multi processor environment. Okay, so these are the two problems.